Hello, everyone. We are Tay, Jay, and Daniel, and we'll be talking about skin cancer classification. One in every three cancers diagnosed as skin cancer, and one in five Americans will develop skin cancer by the age of 70. The two main types of skin cancer are melanoma and non-melanoma. As the name suggests, non-melanoma is a lesser concern because it is non-lethal and can usually be cured with surgery. Melanoma, on the other hand, is a dangerous skin cancer type since it has a high mortality rate. Due to the nature of skin cancer, detecting malignant skin cancer in its early stages is crucial. Classifying skin lesions with the naked eye is a difficult task, therefore, using an AI model to classify helps greatly with the diagnosis process in terms of both speed and accuracy. It is important to note that the prediction from our model is not a ground truth, but instead is a prediction given to doctors who will then go on to give a final diagnosis. Now we pose our research question. How can we use AI to classify whether a skin lesion is malignant or benign?
The general outline of our project is we first preprocessed our data, which we then randomly split into training and test datasets with a ratio of 7:3. We then configured our model to fit our environment. Lastly, we trained our model and ran validation to analyze the results. The dataset that we used for our project is the skin lesion dataset from the International Skin Imaging Collaboration. We randomly selected photos from the benign and malignant image dataset, resulting in a final dataset consisting of 21,845 benign images and 10,561 malignant images. Below are examples of the initial benign and malignant images from the ISIC archive. Since the imbalance in our dataset could result in inaccurate results, we decided to conduct undersampling in order to decrease the size of the benign dataset. So in order to reduce the class imbalance, we decided to use a near duplicate search to delete some of the benign images that were similar to each other. The near duplicate search works by hashing all the images using p-hash. The hash values are added into a KD tree where a nearest neighborhood search is done and images with a similar hash values are deleted. After doing the near duplicate search to reduce the number of benign images, we then randomly chose 10,561 images to match the dataset size with the malignant dataset. In order to further enhance our result accuracy, we preprocessed the data even more by removing the hair and oval from all the images. For the hair removal, we used an OpenCV to remove the hair from the images so that the skin lesion can be better focused. Furthermore, we also implemented oval removal for images that have a lot of black boundaries, as shown in the image on the bottom.
We're going to use EfficientNet as our image classification model. There are normally two kinds of performance enhancement you can get, accuracy and efficiency. In most cases, you'd have to give up one to achieve the other. However, EfficientNet surprisingly improved both accuracy and efficiency in classifying images. There are many model scaling methods, but with scaling, which controls the filter, depth scaling, which controls the layer, and resolution scaling of an image are widely used. When we choose one of each to adjust and let others stay the same, we can notice that they have different trends of increase in accuracy. Older models stick with one of these scaling methods to enhance their performance, but EfficientNet proposed a compound scaling. Under a certain condition, EfficientNet searches for the best depth, width, and resolution for the target dataset using the grid search. With the optimized value, improvement in both accuracy and efficiency is achieved. We use 30% of the entire data as our test data and we'll run through the validating function. Because we're doing a binary image classification, we decided to use F1 score as our metric. Furthermore, because we are dealing with skin cancer and its classification, it is also crucial to consider the precision and recall independently. Our model differs itself from other existing work as we came up with our own pre-processing techniques. Also, we noticed that there aren't many skin cancer classifications using EfficientNet. This further differentiates our work from existing works. This is our training testing environment for our model. We are working with Ubuntu 20, NVIDIA CUDA 10, PyTorch 1.7, and two NVIDIA 2080 Supers with total 16GB VRAM. We configured the model so that the model runs fine on our environment. By trying out different batch, we found out that batch size 24, and it ran through an entire training steps. There are a total of 90 epochs in training with an initial learning rate of 0.1. Learning rate decays by 10 after every 30 epochs. We initially trained the model with unpreprocessed data and achieved an accuracy of 61%. This was to test our model configuration, and now we're currently training the pre-processed data with the same configuration. Because we removed the class imbalance and other features that could distort the data, we're expecting a result better than 61%. Thank you.